One of the next things we're going to speak about with regards to waves is what's known as reflection and wave interference. And they're pretty related. They're two different phenomena, but one results from the other. So it's important first that we understand just some basic definitions. What is reflection? What is wave interference? Well, reflection, hopefully you see here, reflection occurs when a wave hits a boundary between two mediums. So if you have a wave like light that's traveling through air, and then it travels or tries to travel into the ocean, so it's hitting the boundary between the air medium and the water medium, you're going to have some reflection occur. When a light wave hits a mirror, it's also going to reflect. When a sound wave hits a wall, it's going from the air medium to the solid medium, you're going to have some kind of reflection. This reflection will change, the degree of reflection will change based on the two mediums that you're attempting to change between. But that's something we'll get into more detail later. But one way to think about it is if you have a mirror like this and you have a light ray come in, well, once that light ray or that light wave, yellow is probably a terrible color for this, but once you have that light wave hit, it's going to reflect. So you have that ray coming in, it hits, it reflects. Another example would be, let's say you had a wall here and you had a rope and you were shaking this rope up and down. Well, you're going to shake this rope up and down, and after it hits the wall, it's then going to reflect and travel back along the rope this way. Okay, so you get a reflection. That's why you send a wave down, the wave hits the wall and comes back. So reflection, wave is traveling, hits a boundary between two mediums, and at least some portion of that wave will be reflected. Now there's two important things we have to realize. There's two what we call boundary conditions. One of them is called a fixed boundary. And that would be like if you had a wall here and you actually secured a rope to it. So this rope is actually, okay, that did not do what I wanted to. Okay, what's going on here? There we go. All right, so you actually have, this is not, there we go. So you have a rope attached to a wall. And what's going to happen is no matter how much you shake this, it's never going to be able to leave this section. It is absolutely fixed to the wall, cannot move. The other one, which is called a free end, well, if fixed can't move, hopefully you can realize that free can move. And the way we would kind of show this is, let's say you have like a bar or something, and you have some kind of ring. Okay, so we have some kind of ring, and you attach your rope to that ring. Well, if I were to shake this end over here up and down, well, as that wave travels down, this ring, since this ring is not actually fixed, okay, this ring is actually free to move up and down, this ring will also travel up and down. So fixed end, you send a wave down, this is fixed, it's screwed to the wall, it's connected to this bar, you cannot move. Free end is free to move up and down. So just understand fixed and free, and the reason why that's important has to do with how the wave is going to reflect. So if we take a look at this, I believe this is from UCLA, which I can only imagine stands for producer of incredibly uneventful videos that kind of do a good job of showing the physics, but no soundtrack, no sound effects. Kind of creepy when it actually gets that silent, so I'll just stop talking for a little bit. Let's just really amp up the awkwardness. So as you can see, when we have a fixed end, the wave travels along the top, but when it hits the fixed end, you should notice that it actually returns inverted. So that means that when we have a fixed end, a wave will return after reflecting inverted or on the opposite side. So you can see that this wave is being sent down above the equilibrium point, but the second that it reflects, you can see it now travels back along the bottom. If I sent it along the bottom, it would stand to reason that if it reflected at a fixed end, it would return along the top. So hopefully that makes sense as well. Now this free end here is different. This free end is able to move. I assume here it must be attached by, I don't know, a slinky or another spring or something. So this has a range of movement. It's free to move. So if we take a look back at the second case, when a wave is sent down, in this case along the top for a free end, well, the free end is able to move. So whereas the fixed end forces this wave to flip itself around, this free end will continue up or travel up and then travel back down, and it'll actually send the wave back along the same way that it came. So as awkward and silent as this video is, I think it does a good, not far enough, it does a pretty good job. If you watch this free end right here, as that wave travels over, it will move up and it'll send the wave right back. So important to realize, fixed end will invert the wave, it will reflect it over the equilibrium point, and a free end will send that wave right back along which direction, above or below the equilibrium point that it was initially traveling. And that's important to realize moving forward, because we're going to start to see some interesting phenomenon, and that's what's known as wave interference. So if we take a look, well, that stands to reason that here I have some kind of wave. Okay, and we'll say that this wave has an amplitude of 2 meters. Well, let's go ahead and say that I sent this wave down. It's traveling this direction. And let's say somewhere over here there was a free end. Okay, well, the free end should tell us. All right, now let's say there's some kind of ring here or something that allows this end to be free. So this ring is capable of moving up and down. We therefore know that whatever wave is reflected off of this free end is going to be sent back along the same. It's going to be sent along the top, the positive, above the equilibrium point. So if I were to send this wave down, it's going to hit here, and it's going to travel back along with the same amplitude. 2 meters down, 2 meters back. But interesting happens, what if I send this wave down? It reflects, so now this wave is here. Missed, but that's okay. Let's go ahead and say that this is this wave traveling back now, and it has an amplitude of 2 meters. Well, if I were to immediately send another one down, well, what's going to happen is these two waves are going to crash into one another, and that's where something interesting takes place. Now, waves, they do not displace matter. They transfer energy. They don't transfer matter. So whereas you would say, well, two bumper cars could not occupy the same space because matter cannot occupy the same space, two waves can occupy the same space because it's not actually moving matter, it's transferring energy. So hopefully this isn't too profound, but when these two meet in the middle, what you're going to wind up with for a brief moment, they're actually going to combine, and you're going to get an amplitude of 4 meters. So 2 meters, 2 meters, they're going to combine and give me an amplitude of 4 meters. Afterwards, after that happens, they will absolutely continue completely unchanged. So they will both return to the 2 meters that they were initially traveling at, and they'll continue traveling in the directions that they were initially traveling. And this will repeat. If it helps, imagine you have a 2 meter tall person. Yes, I know it's very tall, but 2 meter tall person walking down the hallway. There's another 2 meter tall person walking the opposite way. But when they meet, this guy, I don't know, he doesn't really want to move, so he just lifts the other guy up over his head while he's holding him there for a brief moment. They are 4 meters tall together, but then he puts him down behind him and they each continue on their way. So this is the type of interference. They're helping each other out. They're adding to one another. This is what's known as constructive interference. It's when two waves overlap in such a way that their amplitudes combine and you get a larger wave. So this is known as constructive interference. It's an important term to realize because it's going to start to explain some peculiar phenomena moving forward. All right, well, I think the next logical question would be, well, what if I have a fixed end? What if this cannot move as it could previously with the free end? So I have a fixed end here, and now my rope is completely fixed, so it cannot move. It's stuck there. So if I were to send a wave down that, again, has an amplitude of 2 meters, it would travel down in this direction. This wave would travel along the rope. I'm not going to draw the rope here just yet. It would travel down. When it hit the fixed end, it would reflect inverted. It would reflect on the opposite side. So if I sent one of these down and it reflected and started to travel back along the bottom, well, what would happen if I sent a second wave along the top? Well, what I would wind up with is something that looks like this. Okay, the first wave I sent down would reflect inverted. It would have an amplitude of 2 meters because that's what I sent down initially. But when I send the second wave down, the second wave is now going to overlap with this wave. But one wave is trying to pull it up 2 meters, the other wave is trying to pull it down 2 meters. So what you wind up with is no wave at all. absolutely destructs the other wave. They both destruct one another. And afterwards, both will continue completely unchanged. So you will have the 2 meter still traveling in this direction, and you will have this 2 meter amplitude wave traveling in this direction. Okay, so for a brief moment, they'll pass through one another, they will completely cancel out, and then they will continue to travel on their way. And hopefully, based on the vocabulary I've been using, you can realize that this is called destructive interference. And again, destructive and constructive interference, they're going to help us explain some kind of interesting phenomena. There's a pretty cool YouTube type demonstration, which we'll be learning about coming up, and that's kind of cool. You can show it to anyone, but it's kind of interesting. You don't do anything but use YouTube, and that's kind of cool. All right, but we will get to that. So destructive and constructive interference. The last thing I'd like to go to, whoops, too far. There we go. All right, so just to give you another concrete example, let me find my page. All right, in this case, we have two waves. Okay, one wave has this frequency, the other wave has a frequency in which is perfectly aligned. The crests are aligned with the crests, the troughs are aligned with the troughs. And here's the one thing that tricks most people. They say, ooh, a crest and a crest. Those are going to combine constructively. Oh, a trough and a trough. Those must combine destructively. Important to realize. Are these two amplitudes here? I apologize. Are these two amplitudes here going to add to one another? Absolutely, so you'll get constructive interference. These are both troughs. Are they going to produce a deeper trough, a trough with a greater amplitude, or a smaller amplitude? Well, hopefully you see, since they're both perfectly in sync, they're going to produce a greater amplitude trough, and so on and so forth. So these two that are perfectly in sync are going to result in a constructively interfered wave. So you'll get a wave that has a much larger amplitude. Down here, the crest is in line with the trough, trough with the crest with the trough, so on and so forth. So these will completely cancel out. And you can actually get something in between the two. So if you had some of these that were off-center, sometimes you get these kind of weird waves that kind of have amplitudes that grow and then shrink and then grow and then shrink again. It all depends on how these waves are lined up. So the important thing to realize here, reflection and wave interference. Reflection, wave hits the boundary between two mediums, and it's going to reflect in some way or some portion of it. And wave interference occurs when two waves occupy the same space at the same time momentarily. We have two examples: constructive interference, which is when two waves traveling either both above or both below the equilibrium point. Important to realize you can have constructive interference for two troughs. They just have to be two of the same, two crests, two troughs. They will constructively interfere. Afterwards, though, they will not affect each other in any way. 2 meters before, they combine for 4 meters because they're constructively interfering. Afterwards, they both continue in the directions they were traveling. They're both still 2 meters. They do not actually affect one another except for that one brief moment in the middle. Destructive interference, same thing but the opposite. Two waves that are traveling on opposite sides of the equilibrium point. They will cancel each other out for a brief moment, after which they will then continue completely unchanged. We'll talk about this in more detail, but 2 plus 2 minus 2 gives me 0. It should stand to reason that if this was 4 meters and this was 2 meters, you would get a 2 meter wave, which is still going to be smaller than your initial. So it doesn't always have to cancel out. This is perfect destructive interference, complete destructive interference, but that's not always the case. As you can see here, okay, so constructive interference, you wind up getting a much larger amplitude. Destructive interference, you either wind up getting a much smaller amplitude, or in a case where they're perfectly aligned, you get no amplitude whatsoever because these waves will completely destruct one another, completely destructively interfere.